Hi everyone, today we'll be talking about characterizing the effects of porosity and particle size on thermal infrared olivine spectral features, brought to you by myself, Ryan Glinken, and my advisor, Dr. Carrie Donaldson-Hanna at the University of Central Florida. So a quick little background here. The shape and position of a mineral's thermal infrared spectral features are dependent on several different things, most importantly, the mineral's chemistry, but also on several others such as the albedo, particle size, porosity, which would be the focus of this talk, and near surface thermal gradients. Quick little additional background here on the lunar surface. So it's very different than here on Earth. Obviously, there's no atmosphere. The surface gravity is about 1/6 of that of Earth, and there's powerful intergrain electric fields, mostly due to intense UV flux, due to lack of atmosphere, high bombardment due to electrons and other charged particles, due to the lack of a magnetic field. And all these things kind of build up together to create these very high porosities, a very delicately structured material that's kind of stacked up on top of each other. Think dust bunnies in the corner of your room or something like that. So on Earth, we really don't see these features. So it's interesting to actually try and recreate them in the lab and see how their effects modify our spectrum. So thermal infrared spectroscopy, TIR for short, you'll be seeing that a lot in this talk. It's really only sensitive to the upper hundreds microns of the surface, so the 1/10 of a millimeter. We're talking absolute surface, especially since a sand grain could be 50, 70, 100 microns thick. So we're talking just the upper surface of even a sand grain. So the surface porosity of the lunar surface has not yet been measured. It's incredibly difficult to actually determine these measurements because you can't bring them back to the lab. The second you accelerate in a spacecraft or even just dig into the surface, you've already disrupted that. So you can't bring it back to an Earth-based laboratory to actually do these studies. And unfortunately, they weren't done by the Apollo or Luna programs back in the day. So it's absolutely imperative to properly characterize the effects of porosity on our thermal infrared spectral measurements. And several studies have tried to do this. However, they've all mostly focused on bulk porosity. And like I said, the bulk porosity is not the surface porosity. There could be a very big difference between a sample cup that's, say, a centimeter thick versus that 1/10 of a millimeter at the top. There's a very big difference of those porosities. So studies have shown, though, that porosity and particle size, specifically increasing porosity and decreasing particle size, so the opposites of each other there, show almost identical similarities on the actual spectra itself. However, no one has actually been able to disentangle these effects yet, and hopefully we'll be able to do that with our study. So we have two major science goals here. First off, can you estimate that surface porosity directly from an image? Like I said, it's very difficult to actually get that surface porosity. And then quantifying the surface porosity and figuring out the difference between that and the particle size effects on our infrared spectra. So on the right here, we have a picture of a whole bunch of olivine of different particle sizes. You can see from fine at the bottom all the way to much coarser at the top. So all of our minerals that we're using in our samples here are olivine. They're all olivine. We're not using any actual lunar simulated material or lunar material itself. So we have 5 different particle size distributions here. A less than 45 micron, which is a control. Many other people have used sample sizes like this before, particle sizes like this before. So this basically lets us know that, hey, our spectra looks right and it looks similar to what other people have done in the past. We also did 4 particle size distributions reminiscent of the surface of the moon itself, brought back from Apollo missions. Obviously, like I said, the porosity can't be brought back, but the particle size distributions can. And we're using what is in the literature here for these distributions. So we also have 3 different packing techniques here. So we have a packed sample. Packed sample is just what it sounds like. We pour some of that olivine in there, we compress it, we add some more material, we compress it, we add some more material until eventually it's level with the surface of the lip of the sample cup. We also have a leveled sample, which is an intermediate porosity. So this is, we pour it gently in there and then we simply level it with a straight edge right across the top. And you can kind of see that interesting pattern that it has there. That's due to that. And lastly is deposited. This is the most complicated to do. What we're actually doing on this is we're taking a sieve and holding it off to the side of a sieve shaker. And turning the sieve shaker on, and it shakes it and lets the material rain down. So we're using a sieve size for this of 75 microns. So it lets the material rain down really slowly. It should also be noted that these are bulk porosities at the bottom here. And like I said, porosity increases as you go from left packed to the right deposited. So we then image those samples that we just saw on the left there. And now we're looking at it at 225 times magnification. You can see a little scale bar there. It's quite small, looking at about 0.5 millimeter. And from there, we binarize our images. And you can see this nice little animation here that should convert it there. So this is what we're doing. We're going into Envy, and we are picking a threshold for our pixel values. So pixel values go from 0 to 255. We have some little algorithms and techniques to come up with a central value. And then everything darker than the value becomes black, and anything lighter than that value will become white. And obviously everything that's black, take the ratio of black pixels divided by the number of total pixels, and that gets you the porosity of the sample, the surface porosity of the sample, at least our prediction. All right, so how does that actually turn out? So we calculate our surface porosities in a range of plus and minus 7% from the sample's measured bulk porosity. Obviously, like I said before, bulk porosity and surface porosity, they're not the same thing. Unfortunately, the bulk porosity is our only known or ground truth in this entire part of the investigation. So because of that, we had to base it off something, and we decided that the bulk porosity and the surface porosity, although different, would be a good place to start. So as you can see here, our packed method is suggesting estimated surface porosity is anywhere from 43 to 58%, our leveled from 65 to 77%, and are deposited from 79 to 84%. So here's what a typical thermal infrared spectra looks like coming from Pascal, which we have in our lab. You can see different features here. We have a Christensen feature, which is the CF. The TF is the transparency feature. There's a second Christensen feature labeled CF2. We also have stretching molecular vibrational bands off to the middle/left, and bending molecular vibrational bands off to the right. There is also a gray region here, which has a low transmission due to the beam splitter. There's nothing particularly important there for this investigation, so just to be noted. So then we take that spectra and we stack it with all the other spectra of varying porosity on the left and varying particle size on the right. So on the left and the right, you can see that the spectral features that I was just discussing really do change with different features. So if we look to the left here, we have kind of stacked, packed, leveled, and deposited. These colors will stay the same throughout the presentation. So if you're having a little trouble trying to track something, that's what they're there for. And on the right, you can see the same thing, but with particle size. You can see that the less than 45, which doesn't have any coarse particulates in it, really stands out from the rest of the spectra. So what actual features are we measuring here? I kind of discussed them really quick, but let's make this a little bolder here. So there's a slope leftward of the Christensen feature. We'll be measuring that. There's also the spectral contrast of the Christensen feature, which we're measuring from that peak all the way down to that trough. Then the depth of the third vibrational band, which you're measuring from that trough all the way up to the height of the Christensen feature here. We're also measuring the depth of the transparency feature, which is drawn as a perpendicular line from the trough of the transparency feature, the absolute minima, straight up until we're meeting a line connecting the two peaks on either side of the transparency feature. We're also going to compare it to the area of the transparency feature, which is simply the area between the waveform and that line I just discussed. We're also going to do the 6th vibrational band and the 9th vibrational band. Now the 6th and 9th vibrational bands are actually going to be compared to the height of the CF2, the second Christensen feature, not the first Christensen feature. So for our, what we did after that is we compared how each one of these heights or depths, all these are absolute values, they're all considered positive in the study, and how they compare to each other. So for comparison, this 9th, the depth of the 9th vibrational band compared to the height of the Christensen feature on the left. So you see some plots for that now. So as you can see, on the left, we took a leveled sample and we compared it to all 5 particle size distributions. And we plotted the ratio between the height of the Christensen feature and the depth of that 9th vibrational band that I showed you on that last page. Then we plot them all in a single plot, and then we draw a trend line going through the data. We would obviously also do that for our packed sample and our deposited sample. So we'd have 3 of these plots on the left. On the right, we have a mature Mare sample. Once again, it should be noted that this is not mature Mare on the moon. This is still particulate olivine, but it is modeling after the particle size distribution of the mature Mare regions brought back from soil samples of the lunar surface. So we did the same thing. We picked a particle size, and then we watched how the ratio between those features changed with different porosities. So then we have 5 of these plots. So there'd be a less than 45 mature Mare, et cetera. So we could then stack all those plots together. So on the left, we could stack the 3 porosity samples. So they packed, leveled, and deposited. And on the right, we can do all the particle sizes. And we're going to remove all those data points because it gets real messy real quick. But anyway, we end up with these plots here. So now we have 5 on the left, 3 on the right. You can kind of see, maybe how trends are going, but to make it better, let's put them all in a single figure. All right, so now we have this. So quickly, this is a very complicated figure, but going from left to right or from top to bottom, we have increasing porosity or decreasing particle size. So for example, if you're following the blue dotted line, which is our packed samples, you have increasing porosity as you go from left to right. However, if you go, decreasing particle size, you go from left to right. However, if you take one of the particle size distributions, you'll be varying porosity in that same direction. So in order to disentangle the effects between the porosity and particle size, which is the goal of this study here, you would want to see a dichotomous behavior between the particle size slopes and the porosity slopes. So for example, having all of our dotted line going in a positive direction and all of our dashed lines going in a negative direction, or vice versa. However, from all 49 of our different combination trend line plots, we do not see that behavior anywhere. So we can still do some other things with these plots. For example, just a little discussion here that an intersection between a dotted line and a dashed line is our prediction for one of our samples. So if you look at the dotted yellow line, or orange line is the leveled sample. And if you go to the pink, that's our immature Mare samples. And the intersection of them would be our leveled immature Mare sample. That's our estimate for the model. It doesn't necessarily stand right there, but it will be in that general region. We can also determine from these trendline plots that there are some regions are more difficult to discern than others. So for example, the regions in these 2 areas would be particularly difficult to determine if you say had the ratio between, say, in this case, a transparency feature depth and Christensen feature spectral contrast. If it landed in one of those regions, it would be kind of hard to discern. If it landed in, say, the upper right-hand corner, however, it would be much easier to determine from something else because the lines diverge rather than converge. This region in particular is nearly impossible, at least at this resolution, to determine the difference. So our mature highlands and immature Mare packed samples would be really hard to discern. However, that's only true for that particular plot. When we do other plots, that may not be true. So in this case, this is now transparency feature area versus slope leftward of the Christensen feature. You can now see that the mature highlands and the packed mature highlands and the packed immature Mare are actually now separated by quite a bit. So some preliminary results here. Using our image analysis techniques, we can estimate the surface porosity of our samples. Disentangling porosity from particle size does not appear to be feasible, at least from this study. And we can estimate the porosities of our particular olivine samples of known particle size, or vice versa, using our trendline plots by comparing 2 of our selected thermal infrared spectral features. Once again, it should be noted that this is only working on our particular olivine samples. This wouldn't work on the moon unless you had a whole bunch of samples from the moon. This would have to be reproduced. We have some future work here as well. So next we'll extrapolate these to lunar simulants generated by the University of Central Florida's Class Exolith Lab. So moving from that particulate olivine that we use entirely for this study, and moving to things more reminiscent of the lunar surface. We also begin working on a electrostatics chamber, which would be capable of actually creating, what we hope would be capable of creating even higher porosities than the porosities we were generating via our deposition method. Let us get some more accuracy on those trend lines that we were discussing at the far end. And lastly, we will use diviner data to look at some targeted sites on the moon and see if we can do basically the same study there and say, hey, we have this spectra, where would they fall on these plots now that we have some better information from those lunar simulants. And here are my references. Thanks, guys. Thanks for watching.